Space Drafts is part of an international network of astronomy on tap events where professional astronomers share astronomy with the public in bars and pubs around the world. This is Tucson's edition of Astronomy on Tap. My name is Nick Schragle. I am a third-year graduate student at the University of Arizona doing astronomy, and I'm just here to tell you how this show works. So we're going to have two talks for you today. Each are about 20 to 30 minutes long. In the middle of those two talks, we'll have an intermission for about 20 minutes, and we will also have some news from around the universe, brought to you by two of our postdocs. We will also be having a little bit of trivia in these talks. There will be at least one question in each of these talks. For the person who gets the trivia question right, we have a special prize over here at our merchandise table. Speaking of merchandise, we do have merch for sale, in addition to quite a few free goodies from AAS. We also have Eclipse glasses available over here. If you're not aware, we have an eclipse coming up in April. So if you don't want to burn your retinas, come over and grab some glasses. Now, because we are here at Borderlands Brewing, we are sitting right next to an active train line, courtesy of Union Pacific. So, we have a little tradition here at Space Drafts. Whenever there is a train that comes by and interrupts our speaker, what do, folks? We raise our glasses and we toast the train with a choo-choo.
Choo-choo!
One last thing, don't forget to tip your bartenders, and we will begin with our first speaker. First speaker is Afi Khan. He is a colleague of mine at U of A, a fellow graduate student, and he'll be talking about India's first solar space observatory. Afi, the floor is yours.
Woo-woo!
This is Afi reading for Shakespeare, reading for the character Hamlet. To be or not to be, that is the question.
Afi, it's not the auditions yet.
It's not the audition.
No,
but I
ne-
memorized my lines.
That's next week.
What do I do now?
You signed up for this. You got to talk up there.
Oh, okay. But I memorized my lines.
Hey, next week maybe, but this.
My clicker doesn't work.
That's my fault. Try it now.
I can go back to Shakespeare.
Do it now. Point it at here. Point it at here.
Ah. No, still doesn't. Oh, now it does. So where were we? To be? No, sorry. I'm Afa Khan. I'm a third-year graduate student at the University of Arizona, and I'm doing a PhD in astrophysics. But before I chose this life where I don't get paid enough to do a lot of work, I was working on a space mission back in India, and I helped build India's first solar space observatory, and I'm going to tell you all about it. It's called Aditya L1. It was launched on 2nd September 2023, not 24. Typo. It was my sister's birthday, and she was like, "What are you giving me for birthday?" I said, "Well, a 2,000 kilogram satellite that's going up there. Happy birthday." Well, she was not impressed. She's not an astronomer. It is now located 1.5 million kilometers from Earth, well beyond the orbit of the moon, and this is the first time India was able to insert a spacecraft into what is called an L1 orbit, which is sort of a balance point between the sun and Earth, and that's because we want to look at the sun forever and send our data to the Earth forever. And I'll talk a little bit more about it as we go along. I have to get used to this. So in terms of what science Aditya wants to do, I'll go into the details of this, but the main science objective is to do science that other NASA and ESA space missions have not done. So fill in a gap that humanity has in its knowledge about the sun. And you might be wondering, well, what do we don't know about the sun? It's a star nearby. We should know everything about it by now. Uncle Galileo saw it 400 years ago, and by now we should know everything. The answer is that we don't. And some of the things that we want to understand is how this corona around the sun, which is its atmosphere, is heated, how the energy is transmitted, how do these massive, what so-called coronal mass ejection that you hear a lot about on Fox News every time one happens, and then how does the dynamics of the solar atmosphere couple with what is happening inside the sun, and finally to understand that distribution of that wind and its impact on satellites around the Earth. And that's probably one of the most important reasons, because all of our lives are dependent on these multi-billion, trillion-dollar investment in space, and one solar eruption can actually knock it out. So do we have something that can do a surveillance for us 24/7 and tell us a flare is coming? So this is what happened on the 2nd September. PSLV launched this 2,000 kilogram satellite into orbit, and then for the next 3 months, for almost next 3 months, it was just on a journey to the orbit where it would remain, hopefully, for a very long time. The mission's baseline design is to last for about 5 years, but potentially a mission like this can last for 20 years. Example is SOHO at L1, which was launched several decades ago and is still functional, still sends back data. So basically it did a few loops of the Earth, increasing its orbit gradually by doing orbital burns, and then did one transfer maneuver to get into this very lesser, just like orbit, where it kind of loops around L1, and the size of this loop is about, ask me later, I forgot. Just like I forgot my Shakespeare lines. But it's quite a significant loop, so it doesn't go and sit at a point, but still is orbiting. But if you ask me what, it's orbiting nothing. It's basically being swing like a rope. If you are two people and you spin a rope, and the rope makes a kind of figure, that's the figure that this is making. And the gravity of the Earth and the Sun combination keeps it in orbit, and it has fuel on it that burns and keeps the spacecraft in that orbit by periodically correcting its attitude. And this is how the spacecraft looks like. And these are this spacecraft has multiple scientific instruments, because, well, if you're going there, making a spacecraft and spending 10 years building it, you should not put all your eggs in one basket. So there are multiple instruments. Well, there's a scientific reason for that as well, which is that we want to comprehensively cover different parts of the electromagnetic spectrum and also particle energy spectrum. And I'll talk a little bit more about that. But we want to cover these different regimes of scientific observations, and that's why multiple instruments make a lot of sense. And they are sort of independent of each other, so if even one dies, you have other instruments that can still accomplish part of your scientific mission. So we have a visible emission line coronagraph, VELC, the solar ultraviolet imaging telescope, the star of the show tonight. That's the telescope I helped build. I shouldn't be humble. I designed it. I went up. I was the lead of the system till it went to CDR, and then somebody else built it for me. PAPA, which is a particle counter, SOLEX, ASPEX are both particle counters. There is an in situ magnetometer that measures the magnetic field at L1. So these instruments combined give us a lot of, sorry, I'm gonna go back, yes. A lot of information about the instrument. So the primary payload is VELC, which kind of sits on top of the spacecraft. This is a coronagraph. It basically blocks the disk of the sun and tries to look at the faint gas around the sun in the visible line. That's why the name visible emission line coronagraph. And it will look like something like the eclipse. So it creates an eclipse in orbit, trying to observe this gas around the sun. And it's critical because there are a few things we don't understand about the sun. One of them is the surface of the sun is about around 6,000 Kelvin. But the gas surrounding it is about 2 million Kelvin. And that's called the solar corona, solar atmosphere. There are different terms for it. And we have a gap in our understanding of how this hotter thing is on the outside and it is being fed by this cooler thing on the inside. That does not make sense from the laws of thermodynamics. But when you throw in magnetic field and you throw in complicated gas dynamics, you can make sense of it. But we don't have enough information to solve that mystery. And this is the closest star to us, so kind of weird that we haven't figured that out yet. Then we have, oops, yeah, so that's VLC. Trying to go to the next payload. And that's SUIT. Right next to it, it's a smaller imager. It looks at the sun in the ultraviolet, and by imager it's basically taking pictures, beautiful pictures, but in the ultraviolet wavelength between 200 to 400 nanometer.
Oh, is that it? Did you
And
find it?
it's unique because
Yeah, that's it.
although there have been many solar missions that have
Thank you. Can you
taken
please
images of the
blast
sun
it?
in the full disk, both from the ground and in space, but this 200 to 400 nanometer wavelength has not been covered, and that's because this wavelength is pretty notorious for a lot of reasons, and I can go into those if you are interested. But it's very challenging to build a telescope in that wavelength because the detectors are not good enough, the coatings are bad, and so developing those detector and coating technology took us so much time that somebody could only build an instrument like that in a decade from now. So this is Soot. It looks small, but it's actually almost a meter in the optical in the length. The optical bench is about a meter in length, and this is the aperture door. The door opens, and inside it is just a 2-meter telescope and a detector. And then we have a bunch of filters that basically help us select the wavelength that we are interested in observing. Now, before I go into the details of what Soot does, because if I do that, then I'll do injustice to this audience, I need to give you a little bit of a background. So we live with this star. We live with this one star. We can now, with our technology, look at its surface from Galileo, who looked at the sunspots 400 years ago, to now making videos like this. So this is not Soot or from Aditya, because Aditya is still in its commissioning phase. This is from another similar observatory that went in an orbit around the Earth called the Solar Dynamic Observatory, and observed the sun in a further ultraviolet wavelength at around 304 angstrom. And you can see that there is a lot of dynamic activity going on here, and this is sped up. The sun spins around its orbit in about 15 to 30 days, depending on whether you are at the equator or the pole. But you can see a lot of dynamic activity, and the scientists are curious about how this happens. But before that, I have a curiosity for you, and this is a trivia question. So audience, how much time does light take from traveling from the sun to the earth?
Raise your hand.
Hey, raise your hands. Disqualified. This first time space drafter. Disqualified. I've done 2 of these talks. Just no humble brag. You heard the answer. Come on. There at the back. Gentlemen. No, you have your hand raised. Yeah, sorry. 8 minutes. And why so? Oh, because they have traffic police writing speed tickets. Oh, they have Einstein police who said that, well, light can't travel faster than 300 kilometers per second, and so the sun is about 150 million kilometers. Do the math. I can't. I'm an astrophysicist. I use a computer to do the math. Come on. Trivia question number 2, because I'm feeling generous.
It's not charging. Why is it not?
Today,
I can't figure it out.
well, my clicker is not feeling generous today.
Oh, that's my fault.
No problem.
There you go. Do it now.
After the technical
Ah.
difficulty.
No. No?
No? Trying? Oh, no. Wait. Trivia question
Yeah.
number 2. How much time does the light take to travel from sun's core to us? The person who got the answer right, do you want to take another guess? Still 8 minutes? Are you an astrophysicist?
Not
Did you
thousands.
study? No?
Yeah, more
Okay.
than thousands.
You're keeping up with your, well, thousands of years in the ballpark. Somebody has a better estimate? I'm deliberately ignoring the astronomer. I know you. I know you. You get paid enough to buy those. No, I'm kidding. You don't. Actually, yes. Himansh, please go ahead. This was not a setup. What is the answer? Gets an F in stars. He can't pass his comprehensive
Yeah, it's
exam.
not 10,000.
Anybody else?
I know.
Anybody else? At the back. I wouldn't give it to you. You're close. You want to take another guess? It's 11 million? No. It takes 2 million, so nobody gets it. It's about 2 million years, and that's because the photons that are generated inside the sun because of fusion of hydrogen bounce around a lot because it's very, very dense inside. So before they can come out, they bounce around a lot, and it takes a lot of time for them to come all the way to the top. But I'm feeling very generous today, but my clicker is still not. Is it just me, or is it the clicker? Double or nothing.
No, it should work.
Lady at the back, double or nothing for you. Because you got 10,000 years, it's a long time. How much time does it take for the solar wind particles to reach Earth? Himansh, do you want to pass your stars exam? Anybody? No? Nobody? Guess, come on.
Jeez.
Something else is going on, right? 4 days. It takes 4 days for solar wind particles. The wind is fast, but not as fast as the light. Unfortunately, nobody gets double or nothing, but prize for person at the back over there, for sure. Okay, moving on. So, we know this one star very well, the sun, because we can look at its surface. We can make these telescopes and look at its surface. If I remember correctly, there's now like 10-meter telescope just to observe the surface of the sun. We send rockets, we send balloons, we send these spacecrafts to study the sun because we care about it. But then that's probably it. That's the only real data point we have if you want to understand a star up close and personal. Other stars are almost like point sources, so we don't get a lot of information about them. Of course, people devise clever tricks to understand the stars, and some other day I'll talk about that. But Sun is unique. It's the closest star to us. It allows us to understand its surface, its dynamics, its properties, the magnetic field. All of this complex phenomena let us make models for how other stars would be, and there's a huge diversity of stars. So one star doesn't reveal secret of all stars, but it gives us some clues, and that's why we do this.
That's your problem.
So a little overview of the sun before we dive into the instrument. It has a core in the center where hydrogen is meeting hydrogen, colliding with it and creating helium, and the process, the total mass of the hydrogen that combines together to form the helium is slightly less than the mass of the helium, and that mass disappears, goes into energy according to Einstein, and that energy is the photons that are emitted. And then after bouncing around a lot within the core, they go through this radiative zone where the transfer is mostly photon traversing, then into a convection zone. You can imagine it as a region where the plasma is boiling and stirring up, just like boiling water, rises up, gets up to the surface, cools down, and circulates back. And in the end, there is photosphere, and that's where the plasma becomes thin enough for the photon to just free stream in one direction, and streams in every direction, and that's the light that reaches us in 8.3 minutes from that surface. But that's not it. The sun has an atmosphere, because not only is it a ball of gas, but it's a ball of ionized gas, and it generates magnetic field just like a magnet. And that magnetic field then traps the plasma, and there's a saying in solar physics which says, well, the magnetic field tells plasma what to do, and the plasma tells the magnetic field how to be. So they are like in this whole conundrum of to be or not to be. Oh, damn it, I'm going back to, no, I'm regressing. Damn it. The me in the alternate timeline was an actor. But anyway, so the corona is this hot ball of gas that is being ejected from the sun, because sometimes these magnetic field lines that are on the sun get twisted up and they trap a lot of energy, but at some point they have to break apart. And that breakage releases not only the energy but also the charged particles that are trapped in the magnetic field, and resulting in a surrounding of the sun that is also ionized. And that is what we call as the solar corona. We understand a lot about it. We know that the photosphere is at 5,000 Kelvin. If you go a few hundred miles above that, the temperature kind of remains stable or drops because there is this hot plasma around it. But then at about 1,000 Kelvin, 1,000 kilometers above the surface, the temperature shoots up 10,000 Kelvin, 20,000 Kelvin. Any takers? 20,001? No. 30,000 Kelvin. 50,000 Kelvin. Any takers? No. 60,000 Kelvin. 1,000,000 Kelvin. 2,000,000 Kelvin. In a height difference of about 100 kilometers, 200 kilometers, barely the thickness of our atmosphere of this tiny little planet we call Earth, the temperature goes from few thousand kelvins to 1,000,000 Kelvin. And we don't know why. We haven't completely understood this phenomenon. For a planet, for a star that is right next to us, for all the satellites we've sent to understand it, we haven't really solved this problem. So there is this mystery. If we don't understand our own star, how do we understand, quoting Carl Sagan, trillions and trillions of stars that are out there? So this is an important mystery to solve. Apart from that, sun is also not like a stable thing. Over the year, over an 11-year cycle, it goes through what is called as a solar cycle. And you might hear in the news, the sun is at the maximum of its solar cycle, and there's a threat to the satellites because it's erupting. And basically what happens during the solar cycle is the magnetic field activity on the sun quietens down. There are fewer magnetic loops forming and twisting and breaking and erupting, to a point after a few years where there are a lot of sunspots, there are a lot of these twisted magnetic field lines that are exploding, they're creating this phenomena called flares, prominences, and then it goes back to silent mode. Do all stars do that? Do all stars show this variability? What happens to this variability in the ultraviolet? What happens to it in the visible? These are some of the questions that we try to answer about the sun. Living with this big ball of gas. Still struggling with this flicker. I'm not sure why.
It should be working. There you go.
So, why do we care? I mean, the scientists care because they're like, we want to understand the parameters of the magnetic hydrodynamic simulation so that we can simulate the stars. Never mind. It's related to directly to life on Earth. The auroras are a result of the solar activity. We see this beautiful show in the sky. The ripples in the glows are connected to what is happening on the sun, because these charged particles are hurtled towards everywhere in space, come towards Earth, get trapped in a magnetic field, and then hit the atmosphere and creating these ripples and glows. A few 100 years ago, just this beautiful light show. But a few billion years ago, if Earth did not have a magnetic field, the solar wind from the sun would have ripped off our atmosphere, would not have created a situation that could sustain life, because all the life on the planet would have been polymerized or destroyed by this hard ultraviolet radiation, hard particle distribution, and we would be a barren planet. Today, we care more because your cell phone, the street lights, everything around us is connected to this network of satellites that we have put around. And these charged particle storms can be strong enough that they can knock them out. We already know that they're strong enough that they can also affect infrastructure on Earth. A few decades ago, a nuclear reactor was shut down because of solar magnetic activity, because the power grid yielded. So a strong flare from the sun directed directly towards Earth could disrupt life on Earth. So we care in the modern world about this. I was trying to scare you about this ultraviolet radiation and the magnetic field. Well, the magnetic field is not the only thing that saves us. We also have an ozone layer, which is basically created by the sun and destroyed by the sun. But the balance of this ozone's existence protects us from getting any ultraviolet light down to the surface. The sun is emitting broadly across the spectrum. It emits X-rays, soft X-rays, near ultraviolet, far ultraviolet, and radiation at all different sorts of energy. Only the visible light filters down on Earth, and in fact, we are the ones who have adopted to the light that filters down. Our life is dependent on that, and our eyes adapted over the period of evolution to look at that visible radiation. So if somebody asks you, why do you see only visible light, you can blame the sun. But this picture just shows you that all sorts of radiation is coming down. A lot of it doesn't make down to Earth and is absorbed at different layers of the atmosphere. The ultraviolet specifically is responsible for formation of ozone and destruction of ozone. So it maintains this nice balance of ozone. So if the sun there are activities on the sun that starts making more of this ultraviolet radiation, what happens? The ozone will deplete, and we will get fried by this harmful UV radiation which we have not adapted to. What if it goes down? Similar consequences, the ozone cycle would get disrupted. But more than that, this radiation also deposits energy in different layers of the atmosphere. So if this energy balance, the sun, varies over time, then so can the climate of the Earth. And in fact, we have strong evidence that in the past, major solar events have definitely led to large variability in Earth's climate. And that was one part of the climate change debate, that can you prove that this is because of carbon dioxide and not because the sun is varying? And the scientists raised their hands. Well, we don't know because we haven't observed the sun enough, so we need to send some space mission to observe the sun and tell you whether it's the case or not. But if you are a climate change skeptic, I must tell you, we've spent billions of dollars trying to say, well, the sun is the culprit, we can keep running our gas cars and not worry about it, can't blame it all on the sun. That's not the case. We know to very high accuracy that solar variability is not responsible for the current anthropogenic climate change. So something very interesting. It took many years of research to do this. Let's come back to Soot now. I think I've given you enough background on Sun-Earth connection and how Sun operates to tell you more about Soot. So Soot operates in this band where both the wavelengths where the ozone formation happens and the ozone dissociation happens at a lower level in the atmosphere. So it's trying to understand the sun at the wavelengths, which is key to our existence. Apart from that, it has several scientific objectives that are directly related to understanding the sun better, and directly or indirectly helps us understand, connects it to our existence. So coupling and energetics of the solar atmosphere, as I said, we don't understand how energy transfers from the photosphere all the way to the corona. We're trying to understand that. Dynamics of the solar atmosphere. How do these eruptive events happen? Like, why does it suddenly explode? How much energy is there in an explosion? How many of the large explosions that can knock out our satellites can happen over 100 years or in the next 10 years, just like we worry about asteroids hitting the Earth? Prominence study. These are basically these loops of magnetic field that stay in forever, for a very long time, and don't erupt, and suddenly one day choose to explode and throw out this huge mass of plasma towards anything that is in its way, and we don't understand it very well. So we want to understand the mechanisms responsible for that, how these coronal mass ejections initiate very early, and then how does that affect the space weather, whether it's the assets around the Earth or the astronauts on their way to Mars, or even colonies on the moon. And sun climate studies. How does short-term and long-term variability of the sun in the ultraviolet affect the global climate, and what role does it play in affecting different climate cycles? And that is an important question to answer. How relevant is sun? So how do we do that? So we take, Soot is a very simple instrument. It's a camera, takes an image of the full disk of the sun at a very high resolution so that you can resolve very small features on the surface, at the same time look at this giant disk of the sun. So sun is about a degree in the sky, please correct me if I'm wrong, about a degree, half a degree? Half a degree,
Yes.
half a degree in the sky. And when you talk to astronomers, some of us make these small fields of view which are like a few tens of arcsecond. The people who are looking at planets, they are like trying to be sub-arcsecond, and they don't care about anything outside. So they can make instruments for that. But then to make an instrument that covers an entire very large field on the sky, at the same time maintain a very high resolution is very challenging, specifically in the ultraviolet. So again, let me remind you, this is the full emission from the sun. So all of that is emission from the sun at different wavelength. The peak of the thing doesn't matter much, but if you add all this up, that comes about to be about 1400 watts per centimeter squared, just above the surface of the Earth. We are looking at this wavelength region where there is like a lot of difference from the brightest part to the smallest part, several factors. And we have these filters, which I don't want you to memorize for the test, but maybe I'll ask them anyway. That happens a lot in grad school. But we have these filters, and their role is to isolate different lines. And what do these lines do is basically they look for emissions from different hot ions that are tracer for different activities or different temperatures of the gas. So in the end, what we're trying to do is we have these different ions at different wavelength, and they exist at different temperatures, so and at different altitudes from the surface of the sun. So we want to create an onion peel 3D image of the sun where we can connect different features across the layers and say, oh, this particular emission goes like this, but at this altitude it dies out, or it takes a turn, and the magnetic field, the plasma is following the magnetic field, so that's the behavior of the magnetic field. And from there we could derive probably the magnetic field is somehow taking the energy, breaking up in the higher atmosphere and depositing energy into the corona. One of the hypotheses. And there are several different hypotheses to kind of try and explain why the corona is super hot, for instance. That's one of the science objectives that it tries to address. Now before I move on, oh, where did it go? A geography lesson. Yes, so SUIT is an instrument that was built at what is called as the Inter-University Center for Astronomy and Astrophysics. It's one of the premier national labs, government-funded national labs in India, which purely does astronomy and astrophysics. And this is a beautiful campus where we have a bust of Newton, not sitting under an apple tree, but a banyan tree, because that's India. So no apple falls on his head, but probably a monkey throws one at his head. And then we have Galileo, and we have Aryabhatta, and we have Einstein, who's just looking up, pretending that it was not him who threw the apple. And this is where my office was, right in front of two banyan trees that also the architecture represents two Roche lobes, two stars that are really close to each other, and they are exchanging matter in close proximity. So the architect was one of India's finest architect, Charles Correa, and he thought through about the astronomy theme and kind of created the architecture. Just so that you're not lost, I'll give you a quick geography lesson. This is where I was in India. The city is called Pune. This is Bangalore. This is where the big space agency's headquarters is, and this is Sriharikota, where the rocket was launched. So the rocket was launched. You saw the launch, and the first light happened a few weeks ago in January, and this is the first light image of the disk of the sun. In one of the filters, the list I showed you is the magnesium 2 filter that traces the temperature of the corona, and you can see all these features in there that are being looked at. SUIT is going to do these large images every minute, and it's also going to look at a smaller region on the sun every 4 seconds for next 5 years in 11 filters. That means we'll be generating 20 gigabytes of data every day for the next 5 years at least. And by the rumors that I've heard, we have enough fuel, if nothing else goes wrong, to last for a decade, maybe more. So a lot of data, so a lot of jobs for the grad student. The first light happened because that door opened. That was the biggest worry I had when I was designing this system with a team of 70 engineers. The guys who are making the door, you need to have your A game on. And they did. The door opened, it's a multi-deployment door, it closed back, it opened again, and it can do that 1,000 times so that we can move our instrument, look at the sun, look at other targets, and go on. And then not only did we look at one of the wavelengths, we looked at all these different wavelengths that I showed you, and we have nice, interesting results coming out already. These images still are not super interesting because these are just calibration images. But in the end, we want to create these. So as I said, there are these smaller regions we look at. We want to look at these interesting regions where there is a bright event happening. So Soot not only looks at pre-assigned regions, but if a solar flare happens and the scientists are sleeping, it would automatically lock onto a solar flare and observe it till the solar flare goes away. That kind of onboard intelligence is quite challenging to implement. Trust me, I know. If this video is not playing, could you play? And this is the first dynamic, I think it should, I don't know. It does. This is the first dynamic event, a prominence caught by Soot, already only in its performance verification phase in the first month of operation. We can see these interesting dynamic event that happens. There are two reasons why it doesn't look as brilliant as the Solar Dynamic Observatory. One is the wavelength. At that wavelength, things are more fuzzy. Second is still instrument is not completely calibrated. This is how the satellite looks. It's 2-meter sized satellite sitting on this launch vehicle fairing, ready to be integrated. This is the integration facility, a few human beings for scale. That's the launch vehicle, the PSLV. Still one of the cheapest way to get into space. And that's just the night before we launched. Thank you very much. Question, I only have time for one because I also did the little theatrics for you. Gotta keep science interesting, otherwise you'll not get funding. Ask JPL. Savage, I'm savage. They'll never give me a job. Question.
Are you able to talk to the solar radiation levels involved in the orbital area and the potential impact on the electronics and what's done to mitigate that?
That's a good question. So I'm not an expert at that, but the other.
Repeat the question.
Yes, the question was, can we measure the impact on the electronics? Can we measure the impact in situ, right?
And what's done to mitigate it?
What's done to mitigate the radiation?
Right, lead shielding, or how you getting away from it?
We're significantly far. There are missions that have gone closer, but all the hardware is specially designed electronics that are radiation hardened.
Radiation hardened.
For a very for surviving 20-year mission life. That was my requirement. I want to have electronics and systems and mechanisms.
It's very expensive.
Ask me about it. $200,000 analog to digital converter. This small, real estate. It was in my hand, and I was like, can I run away with it? And then I was like, no, maybe not. So that's the answer. We had specialized electronics to survive that environment, and ISRO has been doing this for a very long time. We have geostationary satellites that do communications for us. 10 years, lifetimes, they already have experience to do such a thing. But that's the answer. Thank you so much.
Alrighty, thank you, Afi. Oh, yeah, I'll take that. Thank you. Alright, so checking the time, it is 8:08, so let's call it 15 minutes for intermission. We will be back here at 8:25. See you then, and come over and check out our merch table. We got some freebies.